section 3.3. This is over differentiation rules. This is a section that you're probably going to become very comfortable with very quickly. In other words, it's going to show us some shortcuts to doing all those long examples that we did in the last section where we were finding the limit of the difference quotient. We're going to have a shortcut method to come up to that same result. It's not going to take a whole page full of work. It might just take one line of algebraic work. So this section, when we finally get to it, which we have finally arrived upon this section, tends to be one that we're all very grateful to finally get to. So this is section 3.3, and this is the differentiation rules. And there's a lot of them, and it might take you a minute to get comfortable with them. This is a very important section. This is something you will definitely rely on in all of your future math classes, being able to differentiate and using all these shortcut rules. So you will become very comfortable with them, and you need to get consistently good at it. So here's some of them. I'm going to call this part A. Shortcut, I'm going to call them shortcut patterns to evaluate the limit, or to evaluate the, let's call them shortcut patterns. Okay, the first one is called the derivative of a constant. The derivative of a constant. Okay, the derivative of a constant. And it says if f of x equals c, and the letter C they use consistently as a constant. Like f of x equals 10. C is just a number. It's a constant. If f of x equals c, then the first derivative will equal 0. So here's an example. If f of x equals 10, your first derivative of that function is 0. If f of x equaled 100, the first derivative would be 0. If f of x equaled pi, pi is a constant. It's just a number, 3.1415, la, 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 la. You take the first derivative, it's going to equal 0. So that is your first derivative rule. Now, also, just to show you another notation, this is not a different rule. This is just the different notation, because they're going to flip back and forth in this book and probably flip back and forth even in your homework. Instead of saying f of x equals c, they might say y equals c, and then they might say d dx or dy dx of c equals 0. Okay, something like that. You might see d dx of c equals 0, which is the same thing as y prime, which is the same thing as f prime of x. So all these notations, I'm going to try to show you more than one notation just so that you are comfortable. This is the same thing, a different notation. So over here, if they said y equaled 10, you could say y prime, there's a prime on that, y prime equals 0. Or you could say d dx of 10 equals 0. These are all your various notations, all your various like shorthand notations of doing the same thing, which is calculating the first derivative. Okay, that's your first rule. Your second rule here is called the power rule. Okay, and it says that if, say, f of x equaled x to the power of n, x to an exponent, where n is like a number, then the first derivative of this function is n times x to the exponent of n minus 1. All right, so that's just kind of the general explanation of how to do the first derivative, nice and easy. So if I show you an example with numbers, this would be, suppose f of x equaled x to the 4th power, replacing the n with the number 4. Then if you want to calculate the first derivative, you're going to put the n in front, you're going to move the 4 to the front, keep the x, and then decrease the 4 by 1, or decrease the exponent by 1, and your first derivative is 4x cubed. So pull the 4 to the front and then decrease the exponent by 1. Now, another notation. This is the same thing. I'm not teaching you anything new. This is just a different way of writing it. Would be they could say d dx of x to the n is n x to the n minus 1. It's the same thing. It's just written in that different format, and they're going to really throw all these at you in your homework also. Now let me do another example to kind of a little, not say a little more difficult one, just a little more challenging, I guess. If f of x didn't equal x to the fourth, but it equaled x to the 3/4, then your first derivative, and I've got that little, put that little apostrophe up there to represent your first derivative, is to pull the 3/4 in front of the x, then decrease the 3/4 by 1. 3/4 minus 1, right? Well, 3/4 minus 1 is what? 3/4 minus 4/4, which is a negative 1/4, right? 3/4 minus 1 is a negative 1/4. Now, how in the world do we write that? Well, what is that? This is 3 over 4 times x to the 1/4, where you make the exponent positive, right? You move it to the bottom. And what is x to the 1/4? The fourth root of x. The fourth root of x. X to the 1/4 is the fourth root of x. Okay, so just trying to get used to those rational exponents. Kind of how do you play with them? And then you have them like this. Okay, they can get kind of fun. Suppose your f of x equaled the square root, and I must have taken this one straight from the book, because I would never dream up anything quite this interesting. 2 plus pi. Okay. X to the exponent of 2 plus pi. I wouldn't be clever enough to come up with something that looked quite like that. So before you take the first derivative, when you have a radical, if your function is a radical, before you actually start calculating the first derivative, go ahead and write this as a rational exponent. So the square root of something is that to the 1/2 exponent. So now, after you've rewritten your original function, when you come in here and calculate your first derivative, you're going to pull the 1/2 out front, then decrease the 1/2 by 1. 1/2 minus 1 is 1/2 minus 2/2, which is a negative 1/2. Okay. You're going to take 1/2 minus 1, right? Yeah. Okay. So 1/2 minus 1 is 1/2 minus 2/2. Yeah. Okay. Which is a negative 1/2. Yeah.
So how can you just pull it out of the term?
Because that's a shortcut rule. That rule right there tells me I can.
Okay.
Okay. That rule tells me that's how to do it. There you go. Following the rule. Okay. Well, of course, this isn't going to fly for an answer. So this is, you never put a negative exponent in your answer blank, right? So this is what? This is 1 over 2 times x to the 2 plus pi to the positive 1/2. Which is 1 over 2 times the square root of x to the 2 plus pi. What do y'all think about that? Isn't that fun? Okay. All right. So it's just, yes, it's the algebra, it's the processing of simplifying. It's like, God, all I want to do is this crazy radical, okay? And when you're playing with radicals, when you're differentiating, taking the first derivative, converting it to a fraction, you do that. You usually convert it to a fraction until you get the first derivative calculated, and then you convert it back out of the fraction back into the radical. Okay, so that's your first two rules. Now our third rule is going to be the derivative of the constant multiple rule. The constant multiple rule, that's what it's called. The constant multiple rule. The constant multiple rule. Okay, this one says if f of x equals c times u, this one's kind of hard to, I don't like this one. I don't like the way this is written, but this is the way you do it. You'll be more comfortable with it whenever we get in here and do it. It's c, take the derivative, du dx. That's kind of weird. I think it would be easier for me to, it'd be easier for me to just do an example. This is not good. This notation is very hard to follow. Let's do an example. This looks bad. Okay. Suppose you have y equaling 3x squared, and you're going to take the first derivative of y. We usually call it y prime, but it's also called dy dx. Okay? Your 3, you just kind of write it down again and leave it alone. That's what the c is. Kind of write the number down and leave it alone, and then take the derivative of the x squared. So you leave the constant, you put the constant down, and then you take the derivative of the variable. So we pull the constant down. Now you're going to take the derivative of the variable. Okay? So I'm going to write it down, and then I'm going to do it. The derivative of the variable would be dx of x squared. So this would be like following the rule exactly. So it turns out you keep the constant and take the derivative of x squared. Well, the derivative of x squared is pull the exponent out front, pull the exponent 2 down in front of your x, then decrease the exponent by 1, which is a 2 minus 1. So this turns out to be 6x. 3 times 2 is 6, and x to the 2 minus 1 is x to the first power. Oh, I can see how that can be so confusing. You'll get good at this, I promise. Let's do another one. That's kind of, I can still see now how that would be a little confusing. Okay, so suppose f of x equal to negative 4x cubed. You want to calculate the derivative. You keep the negative 4 and don't worry about it. You take the derivative of x cubed. The derivative of x cubed is pull the 3 out front and then decrease the 3 by 1. Put the 3 in the front and then decrease the 3 by 1, which is just a negative 12x squared. Let's do another one. You'll get comfortable with it. Okay, suppose you have 1/3 x to the 5th. That's your original function. You're going to take the first derivative. When you take the first derivative, you just kind of keep the 1/3 and just hold it. Hold the 1/3. Then take the derivative of x to the 5th, which is to pull the 5 out front and decrease the 5 by 1 when it's in the exponent location. So that just equals 5/3 x to the 4th. You'll get to where you can do this in your sleep. It's even kind of hard for me to teach it. Okay, then we have, and this is really no big deal, the derivative of the sum. The derivative of a sum. And so if your function, we'll call it y instead of f of x, equals u plus v, then to write it simply, y prime equals u prime plus v prime. Take the derivative of u and take the derivative of v. But this also is saying that dy dx equals du dx plus dv dx. Okay, all these notations. Okay, so in other words, here's an example. If f of x equaled x to the 4th plus 15x, this is a sum. This would be like u, and this would be like v. So you're going to take the derivative of the first one and the derivative of the second one. Okay, so it's really nothing fancy. So to take the first derivative, and be certain you'll get that prime where you can see it, to take the first derivative, you take the derivative of x to the 4th. Well, the derivative of x to the 4th is bring the 4 out front and decrease the 4 by 1. Oh, we've not taken the derivative of 15x, okay. Okay, the derivative of 15x is to keep the 15, right, the constant in the front, and take the derivative of x. Well, the derivative of x, that's x to the first power, isn't it? So you bring the 1 out front and you decrease the 1 by 1. So it's going to say 1 minus 1, which is 0, right? Is 1. So this becomes 4x cubed plus 15 times 1 times 1, right? So this is just 15 times 1. So this is just 4x cubed plus 15. We do that so naturally that I forget that we're even applying the rules. You'll get to the point where you'll forget that you're even applying a rule. Okay, let's try another one. Okay, suppose f of x equals x cubed minus 2x squared plus 5x minus 10. Well, that's a sum of 4 of them, like u plus v plus z plus what r, I don't know, whatever they want to call it if you were to really go to the rule. So you're going to take the derivative of each term. So the first derivative, the derivative of x cubed is to pull the 3 out front and then decrease the 3 by 1. Okay, the second one, the derivative of negative 2x squared, where you're going to just leave the 2 alone, pull the 2 down, or the negative 2 down, and take the derivative of x squared. Well, the derivative of x squared is pull the 2 out front, x to the 2 minus 1, which is an exponent of 1. Okay, now the derivative of 5x. The derivative of 5x is hold the 5, bring the 5 down, and what's the derivative of x? 1x to the power of 0, right? Which is just 1. 1 times x to the power of 0, which is going to be 1 times 1, which is 1. I guess I could do that one more time. It's really hard for me to write all that down. Make myself write that down. I don't know why. Okay. And then what's the derivative of a constant? 0. The derivative of a constant is 0, which is the very first rule we talked about. The derivative of a number, the derivative of a constant is 0. So what do we have now? We have 3x squared minus 4x plus 5. That's the value of your first derivative. Okay, I want you to think for just a minute before I go on to the next example. Think back to day before yesterday. If you were told to calculate the first derivative of this function day before yesterday in class, had we had to take the first derivative of this function, right? What would we have done? Right? Which meant, remember how we did it? We had to calculate f of x plus h. You remember? And then we calculate f of x. We put it in this difference quotient. We prayed that everything canceled out, so you pulled an h and they canceled. Remember all this? Okay, so do you see the shortcut? Okay. That's why people love this section, right? So you will have to know the other method. You will have to. There you go. And I will have to be very definite, very specific on a test. Evaluate the first derivative using the limit of the difference quotient. And I might even give you the difference quotient to trigger you to know, oh my gosh, okay, here we go. Don't get to use the shortcut today. Okay, let's see here. Do I have another good example to give you? Yes, let's do one more example under that rule. So I'm going to kind of stay to the right side of the page to kind of be consistent. Suppose our f of x equals x to the 5th plus 4/3 x cubed minus 5x squared plus 1. Okay, so we're still going with that rule, that sum, the derivative of the sum. Okay, and so we're going to do the first derivative again. Well, the derivative of x to the 5th is to pull the 5 out front and decrease the 5 by 1. And then take the derivative of the next term. Well, you got that plus sign, okay? Write your 4/3 and then take the derivative of x cubed, which is 3x squared. Pull the 3 out front and decrease it by 1 on the exponent. Okay? Now you can see, if you have never taken the first derivative like this before, you can see as I'm going, I'm covering this up. I don't know if you're noticing it or not, but as you're working it, when you're through taking the first derivative of the first one, and then you go to the next one, you want to do it, and then you want to kind of leave it behind and keep moving forward, okay? Don't look back for a few minutes, okay? So this one, you're going to hold on to the 5, actually the negative 5, and you're going to take the derivative of x squared. which is to pull the 2 out front and decrease the 2 by 1, which is 2 minus 1, which is 1. Okay, so I wrote the 5 or the negative 5, and then I took the derivative of x squared. And then on the last one, what's the derivative of 1? 0. The derivative of a constant, the derivative of a number is 0. So what does this equal? 5x to the 4th plus 4/3 times 3x squared is 4, x squared minus 10x. Okay, so the next rule. Uh-oh, where'd it go? Honestly, what is that? Okay, come back. Okay, the product rule. Okay, the product rule. If y equals u times v, now this is the one that might take you a minute to memorize. Okay, the first derivative of a product is uv prime plus vu prime. And the way you hear a tutor or a math teacher, or you're going to learn this in your head, we say the first u times the derivative of the second plus the second v times the derivative of the first. So really what I'm thinking, and you'll hear me say it as I teach it, the first times the derivative of the second plus the second times the derivative of the first. The first term times the derivative of the second plus the second times the derivative of the first. Okay, and you'll learn kind of that pattern. The first times the derivative of the second plus the second times the derivative of the first. And one of those things you'll remember the rest of your life by the time you've gone through Cal 3, okay? So here is an example. This seems like a difficult example, but maybe not. X squared plus 3 times x cubed minus 5. That is a product where u is like the x squared plus 3 and v is like the x cubed minus 5. So the u is replaced by the x squared plus 3 and the v is the x cubed minus 5. So in my mind, I'm thinking, here's the first one and here's the second one. Okay. So I'm going to do the first times the derivative of the second plus the second times the derivative of the first. So your first derivative, and I put the first, which is x squared plus 3 times the derivative of the second. Okay, what is the derivative of x cubed minus 5? The derivative of x cubed is pull the 3 out front and decrease it by 1, and what's the derivative of 5? 0. So it's 3x squared plus 0, so I'm just going to write 3x squared. It's 3x squared plus 0, but I'm just going to write 3x squared. Okay, here's the plus sign from the rule. Here comes the plus sign. That's a product. That's a multiplication. First times the derivative of the second. Then the second, which is x cubed minus 5, times the derivative of the first. Okay, so the derivative of the first is the derivative of x squared plus 3. Well, the derivative of x squared is to pull the 2 out front and decrease the 2 by, so 2 minus 1 is an exponent of 1. And then plus 3, what's the derivative of 3? 0. So it's plus 0, 2x plus 0. I'm just going to write 2x. Okay, 2x plus 0, which I'm going to just write as 2x. So we've taken it. The derivative has been calculated. Now we kind of need to come in here and clean this mess up. So if I distribute this 3x squared times x squared is 3x to the 4th, and 3x squared times 3 is 9x squared. And then I distribute the 2x. 2x times x cubed is 2x to the 4th, and 2x times a negative 5 is a negative 10x. Then a little further, 3x to the 4th plus 2x to the 4th is 5x to the 4th plus 9x squared minus 10x. That is the value of your first derivative, which could have been written dy dx, or it could have been written f prime of x, or it could be written y prime. Okay, all those different versions, that is the value of the first derivative of the function. The product rule. Takes a minute to make that happen. Let's do another one. You're going to do a lot of this, and you just can't do it too quickly. There's a desire when you get good at this to do it really fast, and you lose accuracy, so be really careful that you don't get too quick with this. Okay, so here's one, x minus 1 times x squared plus 3x minus 5. That is a product. It's a product of a binomial. Remember, a two-term polynomial is a binomial, and a trinomial, tri meaning three terms. A binomial times a trinomial. This is like u, and this is like v. So I'm going to do the first times the derivative of the second, plus the second times the derivative of the first, where the first is the x minus 1, and the second is that trinomial x squared plus 3x minus 5. So to take the first derivative, I'm going to do the first, which is x minus 1, times the derivative of the second. The derivative of the second. The derivative of x squared, bring the 2 out front, x to the 2 minus 1 exponent, or x to the power of 1. Take the derivative of 3x. Hold on to the 3, and the derivative of x is 1x to the 0, which is 1. The derivative of a negative 5 is just 0. That's the first times the derivative of the second. Then we got to take the second times the derivative of the first, and I don't think, well, I might have enough room, plus the second, which is x squared plus 3x minus 5, times the derivative of the first. What is the derivative of x? It's 1. It's 1x to the power of 0, which is 1 times 1, which is 1. And what's the derivative of the negative 1? There you go. So what we have, I'm going to clean it up a little bit. So this is x minus 1, and y'all will get so much better at this, times 2x plus 3 plus x squared plus 3x minus 5 times 1. Okay, you'll get to the point where that will become much cleaner, much shorter. Okay, so here's the plus sign. I can do FOIL to these two binomials. I'm through with the derivative. I'm just cleaning up my result. So here if I do FOIL, x times 2x is 2x squared. Outside is 3x, inside is a negative 2x, and last is minus 3. (2x squared plus 1x squared is 3x squared. 3x minus 2x is 1x plus 3x is 4x. And a negative 3 plus a negative 5 is a negative 8. That is your first derivative. Just takes a little practice. You will get very good at it. First times the derivative of the second plus the second times the derivative of the first, and you will get there. Okay, the next one is not difficult, but it seems to be the one that I mess up the most on. Okay. I don't know why I always get this one messed up, but this is the one that I tend to have the most error in. And this one is the quotient rule. And it's not that it's hard, but for some reason, this is the one that most of us have the least amount of accuracy with. I don't know what the deal is. Okay. So if you have a u over a v, then the derivative is the bottom times the derivative of the top minus the top times the derivative of the bottom divided by the bottom squared. The bottom times the derivative of the top minus the top times the derivative of the bottom divided by the bottom squared. So really, if it was Miss Zachary's notation, okay, she would say top over bottom, and she would say the bottom times the derivative of the top minus the top times the derivative of the bottom divided by the bottom squared. Oh my. Low times the derivative of the high minus the high times the derivative of the low. Say it again. Low.
Low d high minus high d low.
Low d high minus high d low over low squared. Oh my goodness. I don't know if I can do that or not. Yes.
Also, if you just start with like the v squared on the bottom and write it like the v.
Start with the v squared on the bottom and then go up. Okay. Y'all can have me so confused. Heidi Lomez. I may never get. That's like some of y'all's last names. I can never say it. Okay. Especially when it has 16 letters in it. Okay. Giving him a hard time back there. Okay. All right. Okay. So I've got to do the bottom times the derivative of the top because, as I said, I'm never very accurate on this one anyway. Okay. Here we go. Well, y'all better watch me close. I could get this so wrong. Okay, suppose our f of x equals x squared minus 1 over x cubed plus 1. All right. So here's the bottom, and here's the top, right? Okay, so here we go. The first derivative. The bottom, x cubed plus 1, the bottom, times the derivative of the top. What is the derivative of x squared? 2x. What is the derivative of minus 1? 0. So it's 2x plus 0, or 2x. It's 2x plus 0, but that's going to look really bad, so I'm just going to write 2x. That's the bottom times the derivative of the top. Minus, that's a subtraction on this one, minus the top, which is x squared minus 1 times the derivative of the bottom. What's the derivative of x cubed? 3x squared. And what's the derivative of plus 1? 0. So this is plus 0, so it's 3x squared plus 0, which is just 3x squared, divided by the bottom, which is x cubed plus 1 squared. The first derivative has been calculated. Make certain you can see your little prime on there. And now the goal is to clean this thing up. So to clean it up, I'm going to distribute the 2x. So 2x times x cubed is 2x to the 4th. 2x times a positive 1 is a positive 2x. Minus 3x squared times x squared is 3x to the 4th, and 3x squared times a minus 1 is minus 3x squared. So this is now, when you distribute this minus sign, this is 2x to the 4th plus 2x, minus 3x to the 4th plus 3x squared. I think that is a lot of the problem, is that minus sign in there. You have to watch the signage on all these terms with that minus sign now in that numerator.
And the product rule, if you get them backwards, they add and they're fine. If you get them backwards,
You're all missed.
that's the whole thing.
Okay, so this is a negative 1x to the 4th plus a 3x squared plus a 2x over x cubed plus 1 squared. And it's not uncommon to just leave the denominator alone in the squared format and just let it go. Now, if you see that if you could factor the top and get some reduction, then you would. But in most cases, that doesn't happen. Well, it does happen periodically, but here it's not going to happen, and you just leave the denominator alone. They don't usually ask you to expand that denominator. All right, get ready for this one. I probably should call that example 1 or something. Let this be example 2. Okay, suppose your f of x equals 5x plus 1 over 2 times the square root of x. Okay, when you see that radical and you're going to take the derivative, you need to convert it to an exponent, a fractional or a rational exponent. So I would redo this right now, 5x plus 1 over 2x to the 1/2 power. This is the top, and this is the bottom. Okay, first derivative. The bottom, which is 2x to the 1/2 power, the bottom, times the derivative of the top. There you go, which is yes, it's going to be just 5. You hold on to the 5, and the derivative of x is 1. And then plus 1, the derivative of plus 1 is plus 0, right? So it's just 5 times 1. 5 times 1 plus 0, which is 5 times 1. That's the bottom times the derivative of the top, minus the top, which is 5x plus 1, times the derivative of the bottom. Well, on the bottom, you keep the 2, you bring the 1/2 And then you decrease the 1/2 by 1. What is 1/2 minus 1? It's a negative 1/2. 1/2 minus 1 is a negative 1/2. All divided by the bottom squared, which is 2x to the 1/2 power squared. Very careful, right? So you got to be careful. Okay, now we have a mess. Okay, 2 times 5 is 10, so this is 10x to the 1/2 minus, I'm not certain why that mess is over there. We got to look at that. 2 times 1/2 is 1, so this is just x to the negative 1/2 power, right? And 2x to the 1/2 squared, 2 squared is 4, and x to the 1/2 squared is x. Two squared is 4, and x to the 1/2, which is the square root of x, squared, is x. Okay, so now what do we have going on here? Yeah, I'm trying to think if I can throw my radicals at this yet or not. I guess not. No, I can't. Okay. So this is 10x to the 1/2 minus, okay, x to the negative 1/2 times 5x. Well, 1 times 5 is 5. X times x to the negative 1/2 is what? I just almost walked to the blackboard. X times x to the negative 1/2. What do? You add those exponents, right? X to the 1/2. Okay. So this is 5x to the positive 1/2. And then 1 times x to the negative 1/2 is just x to the negative 1/2. Ten x to the 1/2 minus 5x to the 1/2 is what? Now 5x to the 1/2. 5x to the 1/2 plus x to the negative 1/2 all over 4x. Now I'm not even certain what I'm going to do with this. Now I really don't know what to do with this. I'm not certain. I have no clue what they're going to want in my math lab. But this is the same as 5 square root of x plus, that's got a negative exponent. That is not good. Okay. We can, let me see if I can find my pencil. What I would do, and I'm pretty certain this is what you're going to do in my math lab, is hopefully you will have a pencil. Okay, I will have a pencil. You know you can split this fraction up, right? Right? So this is 5 square root of x over 4x plus x to the negative 1/2 over 4x. You can split those up, and I'm certain they're going to have you do that.
Exactly. Shouldn't that be like minus x to the negative 1/2?
Did I mess that up? Yes, I did. Thank you. This subtraction should have been right here. Thank you. Right there. It should be negative. This guy should be negative, and therefore this would be subtraction. Thank you. Okay, the first term is good enough because I'm running out of paper. Okay, over 4x minus 1 over 4x square root of x. I think that's definitely acceptable to me. I have no clue what my math lab is going to ask for, honestly. We'll find out pretty quickly, won't we? Yes?
Whenever you multiply the 5x with the x to the negative 1/2, how can it turn out to be 5 to the 1/2?
Right here. This was it, right? This was 5x times x to the 1/2, negative 1/2, right? Think about it. If you had x squared times x cubed to be x to the 5th, what did you do? You added the 2 and the 3, right? So if you have 1 plus a negative 1/2, it's a half. You remember this? You do it all the time. You just add those exponents. So you're just adding these exponents. It gets kind of ugly. This is not, how do I take the first derivative? It's, oh my gosh, what do I do with this result? Okay, what do I do with all these rational exponents? And oh no, man, it's a little bit hairy in there. But it's kind of fun. Just takes a little Just have to remember, and I have to do this too in my head. What in the world do I do with that? Oh, yeah, okay. Add them. All right. So then they have this lovely thing in this section, which is the second derivative. So this is going to be a great big part B to this section. Part B, great big part B. And this is the second derivative. Okay, and I'm going to pause the recording and give you guys a break. We've been going a long time, so let me break this recording for just a minute. All right, so let's talk about higher derivatives. Make certain that pause is off. Okay, and so this is part B. A lot of algebra involved. This is not difficult. The second derivative and above. No, and higher derivatives. There's nothing too terribly detailed here. This will come very, very quickly and very easily. Higher derivatives. The second derivative and higher derivatives. So if we have something like y equaling x to the fifth power, then the first derivative would be bring the 5 out front and decrease the exponent by 1. Then we have the second derivative also. The second derivative is the derivative of the first derivative. So the second derivative is take the derivative of y prime. So the second derivative would take the derivative of 5x to the fourth, which is 5 times the derivative of x to the fourth, which is 4x cubed, or 20x cubed. Really what we do, or what I do in my head, is 4 times 5 is 20 and decrease the 4 by 1. Okay, and you'll get to the point where you do that. You just say 4 times 5 is 20, and then decrease the 4 by 1. But y, second derivative is 20x cubed. The third derivative would be to take the derivative of the second derivative, okay, which would be 60x squared, which is 20 times 3x squared, which is 60x squared. That's the third derivative. The fourth derivative, we don't put 4 apostrophes. They just put the little 4 up here in parentheses. And the fourth derivative would be the derivative of the third derivative, which is the derivative of 60x squared, which is going to be 120x, which is 60 times 2x to the first power, which is 120x. The fifth derivative is the derivative of 120x, which is what? 120. We know it's 120, but the whole process is that it's 120 times 1x to the 0. But x to the 0 is 1, so it's 120 times 1, which is 120. So that's showing all of it, but I want you to be able to just say very soon, very quickly, that it's just 120. Okay, and the sixth derivative would be the derivative of 120, which is 0, because the derivative of a constant, the derivative of a number, is just 0. So there's a bunch of derivatives, or the higher order derivatives. We can do this as far as they need us to do it. And so that just shows you kind of how you go through the process. Now, let's take and do a few more examples now that you have a pretty good comprehension of all these higher order derivatives and just derivatives in general and all these shortcut rules to make doing this a lot easier. Let's take a look at this example here. And the question is going to be to find the first derivative and the second derivative. And there's a very hard way of doing this one, or one that's really quite simple. So here is our function. It's x squared plus x times x squared minus x plus 1 over x to the fourth. And you're supposed to take the first derivative. Well, really, your first thought should be the quotient rule, right? You got a top and you have a bottom. Now, I'm not going to suggest you do this, but I'm going to show you why you don't want to do it this way. So I'm going to do it wrong for a minute and say, we don't like this, we're going to not do it this way. But I'm going to show you the not good way. Okay, the not good way would say to take the first derivative is the bottom times the derivative of the top. What is the derivative of the top? The derivative of the top is the product rule, right? which is the first times the derivative of the second plus the second times the derivative of the first. Wouldn't that be right? Now, can you see how nasty this is going to get? Then you're going to say minus the top times the derivative of the bottom, which is not so bad, divided by the bottom squared. But this part right here, this top, the derivative of the top, oh my gosh, this is like, oh man, I don't want to do this. Okay, whoa! Let's find another way. Okay, so that's like, let's don't do that. So let's think of another way. Suppose I play with this, oh, don't put a prime on it, I shouldn't have done that. Suppose I play with this function for a minute. Suppose I distribute all this out. Then there wouldn't be a product involved, right? So let's do that. Let's distribute this. X squared times x squared is x to the fourth. X squared times negative x is negative x cubed. X squared times 1 is x squared. Now take the x through the process. X times x squared is x cubed. X times the negative x is a negative x squared. And x times 1 is x. Now this still doesn't look very pretty, but we can still work on this. Let me see. This is x to the fourth. We lose the x cubes. We lose the x squareds. So it's just x to the fourth plus x, right? That looks a lot better, doesn't it? That looks a lot better. Now, it can even get a little bit better yet. I could do the quotient rule on that. The bottom times the derivative of the top plus the top divided by the derivative of the bottom. No, bottom times the derivative of the top minus the top times the derivative of the bottom divided by the bottom squared. I can do all of that, or I could rewrite this as x to the fourth over x to the fourth plus x over x to the fourth, right? Which is just 1 plus 1 over x cubed. And we can even make this easier by calling this 1 plus x to the negative 3. I haven't even thought about taking the first derivative yet. We haven't gone anywhere yet. We're just playing. We're just kind of algebraically making this a lot easier. So all I have accomplished, which has been a lot, is to rewrite this as 1 plus x to the negative 3, because the derivative of this is so much easier than the derivative of that huge, ugly rational. So now let's play with the derivative. The first derivative, well, the derivative of 1 is 0, and the derivative of x to the negative 3 is negative 3x to the, hold on, negative 4. Negative 4 minus 1, right? So this becomes just negative 3 over x to the fourth. But you know, which way do I want to work with this when I get ready to do the derivative? Would I rather leave a negative exponent, or would I rather go to a quotient? I think the negative exponent would be a lot easier because this is the quotient rule. So I'm going to leave it alone. I'm going to leave it at negative 3x to negative 4. I'm going to leave it there. So that then when I take the second derivative, because remember that was the question, find the first and second derivative. The second derivative is negative 3 times negative 4x to the negative 5. Negative 4 minus 1 is negative 5. Negative 4 minus 1 is negative 5. So this is 12x to the negative 5. Now, when you write your answer in your answer blank, and I think that my math lab is going to throw a fit about this, it's not going to want you to put a negative exponent in the answer. Okay? I think it's going to say you're wrong. What does it say? Sorry? With an exclamation point or something? Okay, sorry, buddy. You really messed this one up. I think you're going to have to write this with a positive exponent. So your first derivative is with the positive exponent when you present your answer, and your second derivative is with the positive exponent with your answers. So when you get something like this, before you jump in and start taking the first derivative using one of our lovely new rules, you might think for a minute about altering it a little bit to make the taking the derivative a much easier process. Makes a huge difference. Okay, so slow down before you tackle it and have 2 pages of work. Okay, so here's some stuff that you're going to see in your homework. I'm just going to show you from the exercises from the book. This is what your homework kind of stuff looks like. Take the first and second derivative. See all these? Like this one, I'd probably rewrite this as 1/3 s to the negative 2, negative 5 halves s to the negative 1. I'd probably do that when I got ready to take the derivative of it. And of course, when you see these, don't use the quotient rule. Just say that's 1/3 x cubed, 1/2 x squared when you go in. And down here, when you're doing these, it says that two different methods. The first method is use the product rule, which is the first times the derivative of the second plus the second times the derivative of the first. And then the second option is to go ahead and multiply it out and come up with a, I don't know what it'll clean up into, but kind of like what we just did when you multiply it out and get an easier polynomial to take the derivative of. So it's asking you to do it two ways. One is the product rule, and the other is do all the multiplication before you take the derivative. Here's a bunch of quotient rules going on. Number 17 here going down. These are your quotient rules. Except for 21 and 22, you could use a product rule, or you could change it to a quotient rule. Okay. Something like number 25, I think I would rewrite that before I took the derivative as 1 over x plus x over x minus 4 squared of x over x, which would be x to the negative 1 plus 1 minus be x to the negative 4, x to the negative 1/2 power. Things like that you can play with. This one, I'd multiply out the denominator before I took the derivative. Just kind of studying it. So before you jump in, before you really get in there and start taking the derivative, kind of look at it for a minute and see if you can find an alternative to make the derivative a little bit easier. Okay, so further examples, that's number 1. And here's another interesting example that you'll see. So I'm kind of looking at some things that you're going to see in your homework. Suppose they say, here's some given facts. Given to you that u of 0 equals phi, and u prime at 0 equals a negative 3, v of 0 equals a negative 1, and v prime at 0 equals a 2. So they give you all this, and it's like, what in the world are they doing? And then here is the question. They say d dx of u over v. Okay, that's the question. So there's kind of the setup, and there's the question. Just going to show you this is not a difficult question at all. Okay. But I want to make certain you're comfortable doing this. Okay, this is going to be applying the quotient rule, which is the bottom times the derivative of the top, minus the top times the derivative over the bottom by the bottom squared. So if you want to evaluate all this at 0, you would rewrite this v of 0 times u prime of 0 minus u of 0, v prime of 0 over v of 0 squared. And then just plug in all the values they gave you. So it's really not that difficult. It's just a lot of notation. So here, v of 0 is a negative 1 times u prime of 0, which is a negative 3. U of 0 is 5. V prime of 0 is 2. And then just v of 0 squared is negative 1 squared. That looks very foreign, doesn't it? When you just look at it, not as a calculus student, but just kind of glance at it like in passing, it's like, what in the world is that? It's really weird looking. So this is what? 3 minus 10 over 1, which is negative 7. Okay, so that's not a hard question. Okay, it's not a hard question. It just looks strange. Okay, here's an interesting question. I'm going to show it straight from the book. Okay, so number 3. Now look at number 45 in the textbook on page 123. Let's just show it to you, and then I'll transfer it pretty quickly so you won't have to have the book to answer this question. Here here's what it looks like. Looks like a terrible question. 45. Find the tangents to Newton's serpentine. That's what they've kind of named this weird graph. It's kind of cool looking. Graphed here. So find the tangents to this graph at the origin and at the point 1, 2. And here they have the equation. So find the tangents to the line at the origin and at the point 1, 2. So what does that mean? Does anybody know how to translate? What are you getting ready to do?
Find the derivative of that equation.
Find the derivative.
And then
Plug in those numbers, and what will that give you? Slope. Okay? So when you find the first derivative, that tells you the slope of the line. Pick a place on the line, I'll tell you the slope. Then you put the x value in, and that gives you the slope at that point. And then you can actually write the equation of that line. Okay, so when we take the first derivative, we're finding one piece necessary, which is the slope of the tangent line. The first derivative is giving you the slope of the tangent line. And once you have the slope of the tangent line, then you can use that y minus y1 equal m times x minus x1 to write the equation of the tangent line. So this derivative is giving you the slope. So you've got to keep that concept in your mind. You've got to be thinking, what in the world do I do with this question? That's why I'm taking the first derivative. So this is the equation of that line, which they called serpentine, something or another, Newton's serpentine. The equation of that line was 4x over x squared plus 1. We want the equations of the tangent line to this graph, to this curve. I'm going to try to be consistent to call it to this curve at the point 1, 2. At that point, 1, 2. Okay, so the question is to find the equation of the tangent line. To find the equation of the tangent line is to find the equation of just a straight line. To find the equation of a straight line, we do this y minus y1 equaling m times x minus x1. That's the ultimate goal. Well, this point is great. This slope is what we don't have. That slope is where we're missing. That's the missing piece. And to find the slope is where we take the first derivative. Our slope is coming from the first derivative. So I'm going to write the slope of the tangent line is y prime. Okay, you've got to keep the concept in your head. Now, why are we in this section? Because it's giving me the shortcut to take the derivative of this quotient, this rational function, which would not have been fun on Monday, right? Okay, but because we know the quotient rule for taking the derivative, we can do this without it being too bad. So here we're going to go into a bunch of algebra. The derivative is the bottom, x squared plus 1 times the derivative of the top. The derivative of 4x is what? 4x to the power of 0, which is 4. 4x to the power of 0, which is 4. That's the bottom times the derivative of the top, minus the top, which is 4x, times the derivative of the bottom. What's the derivative of the bottom? 2x plus 0, because the derivative of 1 is 0, or just 2x, divided by the bottom squared, which is x squared plus 1 squared. And we really don't want to expand that. Don't do FOIL to that. Just leave it alone. Okay, so let's clean it up now. So if I distribute the 4, this is 4x squared plus 4, and 4x times 2x is 8x squared. So 4x squared minus 8x squared is a negative 4x squared plus 4 over x squared plus 1 squared. And, you know, we could factor out a negative 4, but nothing's going to reduce. It's not going to, you know, and then you get an x squared minus 1, but that's not going to, we're not going to get any cancellation. So leave it alone, whatever. There's the slope of the tangent line, that big old mess, will tell me the slope of the tangent line anywhere on that serpentine curve, that cool-looking curve. We want to know specifically at this point on the curve the slope of the tangent line, so that then I can get the equation of the tangent line. So the slope of the tangent line at that 1 point, 1, 2, the slope at that specific point is taking this big old ugly piece of algebra and putting the 1 in place of the x. Okay, putting the 1 in place of the x. So this is a negative 4 times 1 squared plus 4 over 1 squared plus 1 squared. Oh my, that's a 0, isn't it? Did I do anything wrong?
Well, you can actually factor out an x plus 1, or x squared plus 1. If you look at the graph, the slope does look like it's 0.
1 plus 1 squared.
Well, then we can't write the equation. No, it's, well, yeah, maybe it is. Okay. It is. Very good. I was questioning myself. At that point 1, 2, and I don't have a pencil, the slope of the tangent line is going to be horizontal, which means that slope should be 0, right? That makes sense. So very good. Okay, so it does come out to be 0. 0 over 4, which is 0. Okay, that's okay. So here we go. So the answer to the question, what is the equation of that horizontal tangent line at that point? You have now the slope is 0 and the point is 1, 2, which if this is a horizontal line, you know the answer is y equaling 2. But if you're having a hard time with that algebraically, you can still do this. Y minus y1 equals m times x minus x1. Y minus 2 equals 0, or y equals 2. That is the equation of a horizontal line. And in this case, it's the horizontal tangent line. And that's what they want. It's kind of a weird one, but it works. Okay, let's take a look at another question. That's number 45. I'm going to look at number 49 out of the book, too. Because they have very good questions. They write them quite nicely. So I'm going to look at... no, I'm not going to do the origin for sake of time today, but it should have worked out on that one because it's not going to be a vertical line. It looks like it would have been okay. Okay, so I'm going to let that one go so for sake of time move on. Let's take a look now at number 49. It's number 49, which is going to be on page 123. And let's see what it says. Okay. There it is, way down here. 49. That's enough to make y'all dizzy. Y'all shouldn't look when I'm moving the book around. Okay, find all points on the graph. 3x squared minus 4x, that's a parabola, concave up. Find all points on this graph with tangent lines that are parallel to the line y equaling 8x plus 5. Find all points on this graph, which is a parabola, concave up, with tangent lines parallel to the line y equaling 8x plus 5. So what are we going to do? There you go. We're going to take the first derivative of this parabola, which is the slope of the tangent line, right? And we want the slope of the tangent line to equal 8, because the slope of this y equaling 8x plus 5, the slope of that line is 8. So if they're going to be parallel, the slope of my tangent line must equal 8. So I'm going to take my first derivative once I calculate it and set it equal to 8. So when I take the first derivative and set it equal to 8, I'm going to be doing some algebra. It's going to come up with an x value. Okay, so let's write this down. This isn't a very long question, so we might have to write this down. We'll have no clue what's going on here. So the question says, find all points on the graph, and instead of the graph, I'm going to call it the curve. Okay, because that's kind of been what I'm trying to do consistently. So instead of calling it a graph, I'm going to call it a curve, and I can put graph in parentheses. Okay, the curve being the original equation. Find all points on the graph, fx equaling, here it is, f of x equaling 3x squared minus 4x. 3x squared minus 4x. That's your original curve. Find all points on that curve with tangent lines parallel to y equaling 8x plus 5. Okay, this y equaling 8x plus 5, the only thing I need from that is the number 8, okay, which is that slope of that parallel line. All I need is the number 8 off of that equation, y equaling 8x plus 5. So, we know that the slope from this, that the slope of this is 8, the slope of that line, wherever it is, who cares? The slope of it is 8. So I want my tangent line to also have a slope of 8. So I need to find the slope of my tangent lines. And then when I find that slope, I'm going to set it equal to 8. Okay, so this is not bad. The slope of the tangent line is just the first derivative. And the first derivative of 3x squared minus 4x is 3 times 2x minus 4 times 1. The derivative of x is 1. So the first derivative is simply 6x minus 4. That is the slope of every tangent line to that parabola. Okay, it's an expression until I put an x value in it. Okay, so that is the slope. Now, if I want the slope of my tangent line to now be parallel to this line, then its slope must also be 8. Its slope must be 8. So I set the slope of the tangent line equal to 8 because I want it to be 8 so it's parallel to the other line. So then I have an equation here that I can solve. So if I add 4 to each side, 6x will equal 12 and x will equal 2. So now what does that mean? There you go. Now we got to look at the question. Find the point or points where this would be true. So the points that we're looking for is having an x value of 2 in my original line. So here's my x value of 2. Here's my f of x equaling 3x squared minus 4x. And if I put a 2 in there, it's 3 times 2 squared minus 4 times 2, which is 3 times 4, which is 12 minus 8, which is 4. So the point is 2, 4. So evidently we only have one point where the slope is 8. And that would make sense. Okay, that would make sense. So think about this. If you have a, I have no clue where this parabola is. Okay, but if you just have a parabola, okay, if you have a parabola and you want a slope of 8 for your tangent line, it's a positive 8. Every slope on this side of the parabola is negative, right? Every tangent line is going to have a negative slope, so the only place it's going to be a positive 8 is going to be over here somewhere, and that over here somewhere is right here at 2, 4. That's the only place where you have a positive slope, much less a positive slope of 8. Cool. Okay. Y'all act like we're running out of time. Are we? What time do we leave here? 3, right? Okay, so we got a little more time. Good, because I want to do another example. This is my last example, so y'all be happy. All right, so let's take a look now at number 51 on page 123. This is kind of like the last one that we just did. And it says, down here at the very bottom of the page, find all points on the graph of y equaling x over x minus 2 with tangent lines perpendicular to the line y equaling 2x plus 3. So it's almost the same question, but instead of being parallel, it's perpendicular. So almost the same question, but we're looking at perpendicular. So find all points, and there might only be one. Find all points on the curve or the graph. And the given curve was a rational. It was y equaling x over x minus 2. Y equaling x over x minus 2. There it is. with tangent lines perpendicular to the line y equaling 2x plus 3. Okay, so this linear graph y equaling 2x plus 3, which is just a straight line, its slope is 2. So a perpendicular slope to it would be what? Negative 1/2. Okay, so our lines, our tangent lines to this curve, which we're going to do by the first derivative, we're going to set it equal to 1/2. So now, how do you want to do this? Y equaling x over x minus 2. You know, we could write that as 1 minus x halves or 1 minus 1/2 x, couldn't we? It'd be a lot easier. You can use the quotient rule. We'll just use the quotient rule. Why not? That's the hard one. I'll do the hard one to give you all a little practice. Okay, bottom, x minus 2 times the derivative of the top. What is the derivative of x? 1. Minus the top, which is x, times the derivative of the bottom, which is 1. The derivative of x minus 2, the derivative of x is 1, and the derivative of 2 would be 0. So 1 plus 0 is just 1, divided by the bottom squared. So this is x minus 2 minus x over x minus 2 squared, which is just a negative 2 over x minus 2 squared. That is the slope of the tangent line anywhere on the original curve. Give me an x value, and I'll tell you the slope of the tangent line at that x value. So we want this slope of our tangent line to equal a negative 1/2. So we're going to take the slope of the tangent line, which is negative 2 over x minus 2 squared, and we're going to set it equal to a negative 1/2, so it's perpendicular to that crazy 2x plus 3 line. And how do we do this? Cross multiply. Negative 2 times 2 is a negative 4, and a negative 1 times x minus 2 squared. Well, we can kill those two negatives and just make it positive 4 equaling positive 1 times x minus 2 squared. Okay. Now, if I take the square root of both sides, right, then I get 2 equaling x minus 2. And then x would equal what? Equal what? Not 0. It's 4, right? Okay. So the point is 4 something. That's the answer to the question. This is the point. I got to find the match with an x value of 4. So back to this is the point on the original curve. Not the point on this 2x plus 3 line, but the point on the original curve. So the point on the original curve, evaluated at 4, would be 4 over 4 minus 2, which is 4/2, which is 2. There's the point on the original curve who would have a tangent line with a slope of a negative 1/2. Okay? Cool questions, guys. Those are some really, somebody who really worked hard to write y'all some good questions in this book. That is the end. Y'all don't freeze to death in this rain on our lovely winter day. And we have a question in the back of the room. Yes. Move the paper this way, right? Okay. Y'all have a wonderful weekend.